This is the introduction to the Bomb Calorimetry experiment, in which you will determine the heat of combustion of a sample of diesel fuel. Specifically, your goals are to use your thermocouple to monitor small changes in temperature during the course of a combustion reaction, to use a combustion reaction of a sample with a known enthalpy of combustion to measure a calorimeter constant for the bomb calorimeter, and then to use that calorimeter to find the heat of combustion of an unknown sample of diesel fuel. First, some points about gas cylinder safety. You're going to use a compressed gas cylinder of oxygen in this experiment, and so a gas cylinder is a fairly dangerous piece of equipment if not used properly. If used properly, it's very safe. So it has inside it high pressure, and so any damage to the cylinder or the fittings can be pretty dangerous. So you need to make sure that the cylinder is secured to the wall or to the lab bench, and that all the connections are made well and are tight. The cylinder will have a regulator on it when you show up, and what the regulator is there to do is to show you how much gas is in the cylinder and control how much gas flows out of the cylinder. The regulator is attached to a tank valve, which comes straight up out of the top of the cylinder, and this is what keeps the gas in. When you open it, it sends gas into the regulator, but not necessarily out to your experiment yet. The regulator that you have on your oxygen tank is going to look different than all the other ones in the lab. It's going to look like this. So the small gauge that coming off the side of the fitting is the tank pressure gauge, and this tells you how much oxygen is left in the cylinder. You'll want to keep an eye on that so you don't run out in the middle of a trial. The large gauge on top of the regulator is the output pressure gauge, and it tells you what pressure of oxygen is leaving the regulator. For this experiment, you want to fill your bomb to about 30 atmospheres, so the needle should be roughly straight up and down. The knob coming straight out of the regulator is the output pressure control. So turning this knob to the left increases the pressure leaving the regulator. Turning it to the right decreases the pressure leaving the regulator. You also see a fitting. It looks like a little disc with a hole in the middle. This is the fitting for actually putting oxygen into the bomb. And we'll talk in a minute about how to use that. So what the bomb looks like, there's a schematic from your textbook on the left. And basically what it is a piece of steel, a steel container, inside of which are some hooks that from which you can hang a fuse wire, and then there should be something to hold the sample. In the illustration on the left, there's actually a sample cup. In our bomb, you're just going to pipette your sample directly into the bottom of the cylinder, and it'll just sit there. This bomb itself has 4 parts. There's the cup, 2 collars, and a top. And on the top, you can see there are a couple of posts coming out of it, and then on the bottom side, there are a couple of hooks. The hooks are where you attach the fuse wire, and your TA will show you specifically how this works in lab. The posts coming out the top are for 2 things. One is to make electrical connections, and the other is to fill the bomb with oxygen. So when you fill the bomb, you're going to take that fitting that I talked about previously that's on the end of the tube coming out of the oxygen regulator, and you're going to slide it over the top of the taller post on the bomb. In the middle of that taller post, there's a tiny hole, and that hole is where the oxygen is going to go into the bomb. So you'll slide the fitting down over the hole until it covers that hole, and then you'll apply oxygen to the system, fill the bomb, turn off the oxygen, and close the fitting. Again, your TA is going to go through this in detail with you. The bomb goes inside the calorimeter, and this is a schematic view. Yours is going to look pretty different. But basically, the calorimeter has in it a flask to hold water, a stirrer, some sort of temperature measurement, and then all of this is encased in a large steel container. The idea is to keep the system as adiabatic as possible. So bomb calorimetry, I just mentioned, is an adiabatic process. It's also a constant volume process, as you might guess by the fact that this reaction is going to happen inside of this tightly sealed steel bomb. The volume will not be able to change. From thermodynamics, we know that constant volume processes measure reaction energies, whereas constant pressure processes measure enthalpies. So for this constant volume process, since we said it's adiabatic, we know that Q should equal 0. And so delta E for the reaction should equal 0, meaning that the overall energy change is equivalent to the overall energy that causes a temperature change in the surroundings, in this case in the water. So it's kind of strange to think about bomb calorimetry, a combustion reaction, as being adiabatic. It may help to think of the combustion as a two-step process, one adiabatic step followed by a non-adiabatic step where heat moves around. So in the adiabatic step, the combustion reaction happens, and the products are at a final temperature that's higher than the initial temperature. So the energy has not left the system, it's just heated up the products. The part where the heat moves around is when those products cool down back to the initial temperature, and in the process raise the temperature of the water that's around them. So measuring the temperature of that temperature change of the water, we can figure out how much heat is moving around, and therefore how much energy was produced during this combustion. So to be able to do this, we need to be able to measure the temperature first of all, but second of all, we need to figure out what the heat capacity of the system is, so that we can figure out the relationship between a temperature change and an amount of energy. So the system consists of the bomb, which is a little piece of steel. It's going to be 500 milliliters of water in a Dewar flask. There will also be some excess oxygen left over after the reaction, which, if we use the same amount of products, should be the same every time. There's also the stirrer, the thermometer, various other components of the system. And what they all have in common is that we don't know the heat capacities of any of them very well. What we can do is introduce a known amount of energy into the system and measure the temperature change as a result of that known amount of energy. And what this will give us is what's called the calorimeter constant, the heat capacity of the whole calorimeter system, everything that's involved. So we're going to do this using a sample of cyclohexane, which we know the energy of combustion very well. We're going to combust a known mass, and we're going to get out a known energy, and we'll measure a temperature change. Dividing the energy by the temperature change will give us CV, the constant volume heat capacity of our calorimeter. Your results are going to look something like this, and this is a figure from your textbook. What your results look like will depend on how well your system is sealed, whether the system is really adiabatic or not. At any rate, what you're looking for is delta T, the difference in temperature between the system before ignition and the system after ignition. Once you know the heat capacity, you can measure the temperature change for combustion of your unknown sample, and you immediately, with one simple step of algebra, have the energy change from that combustion. We don't want the energy of combustion, though. We want the heat or enthalpy of combustion. So we need to use the relationship that's shown here. Delta H is approximately equal to delta E plus delta N times RT. And the approximately equal is because here we're making the assumption that the system follows the ideal gas law. Delta N is the change in the total number of moles of gas in the system from products minus reactants for the combustion reaction. So this is where we need to use our knowledge of stoichiometry. So delta N depends on the balanced chemical equation for the combustion, before and after products minus reactants. We're going to have to assume something about the average composition of diesel fuel, namely that it has the average molecular formula C13H23. There are, of course, bigger molecules and smaller molecules and non-straight chain hydrocarbons, but we're going to assume that this is a good representation. We can take the balanced chemical equation for the combustion of that molecular formula to find delta N, number of moles after the reaction minus number of moles before. So an example of this is one for biodiesel, because I'm not going to just do the diesel one for you. For biodiesel, if you make it from olive oil, the oleic acid methyl ester that you produced has the formula C19H36O2. And so if we want to find delta N for this reaction, we need to balance the combustion reaction for that hydrocarbon. All right. Balancing this gives us coefficients of 19 and 18 for the products and 27 oxygens for the reactants. Oleic acid doesn't matter because it's not a gas. So delta N, we add 19 and 18, subtract 27, and we get 10. So delta N is 10 moles of gas. Your goals for the experiment, again, you're going to use your thermocouple to monitor the temperature change over this calorimetry experiment. If you have a MATLAB program, this is going to be a lot easier. If your MATLAB program is not working yet, you're going to need to very quickly write voltages off the multimeter as the experiment proceeds, and then convert them to temperatures later. You're going to find the heat capacity of your calorimeter using cyclohexane as a reference standard, and then you're going to find the energy and then enthalpy of combustion of diesel fuel and compare it to a literature value.